Hi everyone. We already saw two modules regarding number theory concepts such as basic concepts, prime numbers, composite numbers, and in the last module we have seen about famous conjectures in number theory and how prime numbers are distributed among natural numbers. Today we are going to see about Dirichlet conjecture, and first we will explain about Goldbach's conjecture. That is, every even number greater than or equal to 4 is a sum of two primes. For example, we see that 4, it can be written as 2 plus 2, 6, 3 plus 3, and 8, 3 plus 5. And 10 is an even number, it can be written in two forms, 5 plus 5 and 3 plus 7. And improved version of this conjecture is that every even number greater than or equal to 8 is the sum of two distinct odd primes. Neither Goldbach's conjectures or its improved form has been proved or disproved. That means that it is not until proved by anybody, but it is generally felt that the conjecture must be true, though all even numbers up to 33 into 10 power 6 have been verified and found to be correct. This conjecture is true for up to the number 33 into 10 power 6, but no normal proof is available till date. So next we will see a theorem which leads to a definition of Mercenary number. That is, if p greater than 1 and 2 power p minus 1 is prime, then p is itself a prime. Let me see the proof. We are given that 2 power p minus 1 is a prime number. Prime number means it has only two divisor, 1 and itself. Now we have to prove that p is also a prime number. Suppose that p is not a prime, then there exist positive integers m, n, both are greater than 1, such that p is equal to mn. P is not a prime means it should be a composite number, so this is possible. Now consider the expression 2 power p minus 1, which is equal to 2 power mn minus 1, which can be rewrite as 2 power m the whole power n minus 1 power n. That is 2 power m minus 1 into 2 power m the whole power n minus 1 and so on. This is because of binomial theorem. And we observe that the two brackets, one is 2 power m minus 1, another term is 2 power m the whole power minus 1 and so on. The two brackets are positive integers because they are having the expression of product of 2, that is power of 2 minus 1. And naturally 2 is greater than 1, so the power of 2 and the additions or subtraction, everything will be greater than 1. So the two brackets will be definitely an integer and greater than 1. And also we observe that m is a divisor of p, so it should be less than p. So 2 power m should be less than 2 power p, and 2 power m minus 1 should be 2 power p minus 1. And it is the product of two integers, and both are greater than 1 and both are less than 2 power p minus 1. So 2 power p minus 1 having factor which is less than 2 power minus 1 and greater than 1. So this leads to a contradiction because this tells us that 2 power p minus 1 is a composite number. Hence, there is a only way that p must be a prime number. So our assumption is wrong. So if 2 power p minus 1 is prime, then p should be a prime number. But there is a remark that the converse of the theorem is not true. That is, if p is a prime, then 2 power p minus 1 need not be a prime. For example, corresponding to the prime number p equal to 11, we see that number 2 power p minus 1 is 2 power 11 minus 1, which is equal to 2047. It can be written as the product of two numbers, 23 into 89. So it is a product of two numbers which are less than 2 power 11 minus 1. So they are divisors for 2047 other than 1 and 2047. So it should be a composite number. So it is not a prime number. Hence the theorem, if 2 power p minus 1 is prime, then p is a prime, is true. But if p is a prime, then 2 power p minus 1 need not be a prime. If it is so, that is, if p is a prime and 2 power p minus 1 is also a prime, then it is called as a Mercenary number. It is defined by the famous mathematician Mercenary. And we already explained that if 2 power p minus 1 is prime, then p is a prime, but the converse need not be true. So all Mercenary numbers need not be a prime number. There are only 23 Mercenary primes known so far, and they are corresponding to the given following prime numbers, that is 2, that is m2, m3, m5 and so on are prime numbers. And for m equal to 4 or m equal to 11, they are not prime numbers. These values of p give all the 23 Mercenary primes and corresponding to p less than 12,000. Till recently, the largest known Mercenary prime number was m 11,213 and it has 3,375 digits. After the advent of sophisticated computers, the 24th Mercenary prime number has been found recently and it corresponds to prime number 19,937 and it is the largest prime number till date. It is an open problem whether the number of Mercenary primes is finite or every odd prime which is greater than 3 can be put in the form 6m plus 1 or 6m plus 5 where m is a positive integers. We are seeing these kind of theorems which leads to prove the Dirichlet conjecture. So let me explain the proof. Let n be a positive integer greater than 3. Then we all know the famous division algorithm, that is, it is also known as Euclidean algorithm. By that algorithm, there exist two positive integers p and q such that n is equal to 6q plus r where 0 less than or equal to r less than r. That means put r is equal to 0, 1, 2, 3, 4, 5 so that we get n is equal to 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. We observe that among these 6 numbers, 6q, it is multiple of 6, 6q plus 2, it is multiple of 2 into 3q plus 1, product of two numbers. 6q plus 3, it can be viewed as a 3 into 2q plus 1 and again 6q plus 4. So these are, by our assumption, by observation, we see that they are composite numbers corresponding to any integral values of q. So the only left values are 6q plus 1 and 6q plus 5. They both are prime numbers because it cannot be written as the product of two numbers. It may be prime or composite. And also we see that, we know that 2 is the only even prime number and it cannot be in the form 6q plus 1 or 6q plus 5. So therefore, any prime greater than 3, it should be of the form either in the form 6m plus 1 or 6m plus 5. And we see and remark that if we replace that m by m minus 1, we can see that 6m plus 5 can be written as 6 into m minus 1 plus 5, that is 6m minus 1. That is, we should see that 6m plus 5 can be seen as a 6m minus 1 also, because here we should not strict on to the notation 6m. We should view it as multiple of 6 plus 1 and multiple of 6 plus 5. So 6m minus 1 and 6m plus 5 both are equivalent form. Now we see and note that 6m plus 1, 6m plus 5 need not be a prime number. For example, if you take m equal to 4, 6m plus 1 is nothing but 25. It has divisor 5, 25 and so on. So it has more than 2 divisor, it is a composite number. Similarly, if m equal to 5, we got a 6m plus 5 as 35, which is also a composite number. Now we will see a theorem. The product of two numbers of the form 6m plus 1 is again of the form 6m plus 1. This is also very easy proof. So let me explain the proof. Consider two numbers p and q of the form 6m plus 1. So it can be written as 6a plus 1 and 6b plus 1, where a and b are any natural numbers which are both in the form 6m plus 1. Now consider the product pq. So pq is nothing but 6a plus 1 into 6b plus 1. What are they? 6a into 6a is 36ab, 6a into 1 is the 6a, 1 into 6b is 6b plus 1. It can be rewrite as 6 into 6ab plus a plus b. Here we use the notation k for the number 6ab plus a plus b. So pq can be written as 6k plus 1, 6 into k plus 1. So it is of the form 6m plus 1. Hence the pq, that is product of any two numbers in the form 6m plus 1, is again of the form 6m plus 1. So similarly, we can prove that the product of two numbers of the form 6m plus 5 is also of the form 6m plus 1, but product of two numbers of the form 6m plus 5 is not again of the form 6m plus 1, is again a number of the form 6m plus 1, but the product of two numbers of the form 6m plus 5 is not of the form 6m plus 5 but of the form 6m plus 1. by using the same methodology. If we multiply two numbers of the form 6m plus 5, for example 6a plus 5 into 6b plus 5, by calculating we finally get the last number will be 5 into 5, 5 5s are 25, and 25 again can be written as 24 plus 1. So 24 is again a multiple of 6. So it will be give a result that 6m plus 5 numbers of the form can be multiplied and gives the result in the form 6m plus 1. These results can be proved for the forms 4m plus 1 or 4m plus 3, where m and m is the positive integers. The following notes, important notes, that an integer of the form 4m plus 3 is equivalent to an integer of the form 4m minus 1. Again, we see that 3 can be written as 4 minus 1. So 4m plus 3 can be viewed as 4m plus 4 minus 1. So that is equivalent to 4m minus 1. An integer of the form 4m plus 1 or 4m plus 3 need not be a prime. As in 6m plus 1 case, we can substitute m equal to 3 or m equal to 4 or m equal to 1. If we substitute m equal to 2, then 4 2s are 8 plus 1 9. So it is not a prime number. So similarly, if we substitute some values for m in f 4m plus 3, we see that 4m plus 3 for all values of m need not be a prime number. So for certain values only, these forms will represent prime numbers. So now we will see gap theorem. That is, there exist arbitrary large gaps in the series of primes, because our ultimate aim is to find how many large primes are there, what is the largest prime, what is a prime numbers list, like that, how it behaves. So here is a theorem. It tells that there exist large gaps between the primes. That is, it can be restated as, given any positive integer, there exist n consecutive composite numbers. That is, we can find, if you find a prime number, after that we can find n number of consecutive composite numbers, so that the next prime will exist after a long gap. Now we will see the proof. That is, let n be an integer. Consider a series of numbers. The first number is n plus 1 factorial plus 2, n plus 1 factorial plus 3, and so on, n plus 1 factorial plus n plus 1. As we are starting from n plus 1 factorial, and also we are starting from 2. So there are n numbers in this series. Why we are saying that these are the composite number? Because n factorial is nothing but 1 into 2 into 3 into up to n. But n plus 1 factorial is nothing but 1 into 2 into 3 up to and so on, n plus 1. So in the expression n plus 1 factorial, there is a 2, and plus 2, there is a 2. So we can take 2 as a common. So 2 is a divisor for first number. So it definitely having more than 2 divisor, that is 2. So the next number n plus 1 factorial plus 3 will have 3 as a divisor. So we are concluding like this. These numbers are respectively divisible by 2, the second number by 3, 4, and so on, n plus 1. So they are composite numbers. Thus we get n consecutive composite numbers corresponding to any given natural number n. So there is a gap between the largest prime less than n plus 1 factorial and the next prime. As n becomes larger and larger, this gap also becomes large. So there is a big gap in the series of primes. Hence the theorem. Next. So next theorem, if n greater than 1 and a power n minus 1 is prime, and then we get a equal to 2 and n is a prime. So proof, first we have to prove the two results, that is one a equal to 2 and another one n is prime. So first we are going to prove that a power n minus 1 is prime. So to prove a equal to 2, suppose a is greater than 2. What is that? A minus 1 will be definitely greater than 1, and also you see the binomial expansion, that is a power n minus 1 can be written as a minus 1 into a power n minus 1 and so on. So it can be written as product of two numbers, and a minus 1 is one of the factor. So it should be divisor of a power n minus 1, which is greater than 1. So a power n minus 1, it is cannot be a prime number because of the fact a is greater than 2. So this is wrong assumption. So a should be less than or equal to 2. So a less than or equal to 2 means only two possibilities, that is a equal to 1 and a equal to 2. If a equal to 1, then what is a power n minus 1? It is 1 minus 1, 0. 0 is not a natural number, so this is not possible. So therefore a must be 2. And next our result is, we want if a power n minus 1 is prime, then n should be a prime number. So for that we are assuming that a power n minus 1 is prime. We already proved that a equal to 2. So that is 2 power n minus 1 is prime. Now we have to prove that n is prime. Suppose n is not a prime, then it is a composite number. It can be written as pq, where p and q are both greater than 1 and less than n, because they are divisors of n and they are integers. Again, using the same argument, using the binomial expansion as in the theorem after the Goldbach conjecture, we can also conclude that 2 power p minus 1 divides 2 power pq minus 1. So that is 2 power p minus 1 is a divisor which is greater than 1, and also it is a divisor of 2 power n minus 1. This leads to us that 2 power n minus 1 is a composite number, which is a contradiction to our hypothesis that 2 power n minus 1 is prime. Why it is so? Because our assumption n is a prime is wrong. Hence n should be a prime number. Now we are proving next result that if a is greater than or equal to 2 and a power n plus 1 is prime, then a should be an even number and n is the power of 2. Proof. Suppose a is odd, then we know that power of an odd number is again odd number, and if you add with 1, then a power n plus 1 is clearly even number. So an even number is divisible by 2. So it cannot be prime number because it is having divisor other than itself. So this is a contradiction to the hypothesis that a power n plus 1 is prime. So a must be an even number. Next, suppose n is not a power of 2, then it should be a combination of odd number and even number. So it should have an odd factor. Let n equal to pq where q is odd. Now next we consider the expression a power n plus 1, that is a power pq plus 1 by a power p plus 1. It can be written as a power p the whole power q plus 1 divided by a power p plus 1. But a power p is nothing but we are taking as some x for a convenient purpose. X power q plus 1 divided x plus, again using the binomial expansion, it can be written as x plus 1 into x power q minus 1 minus x power q minus 2 plus and so on. In the denominator we are having x plus 1. So x plus 1 will get cancelled. So we are having the expression x power q minus 1 minus x power q minus 2 and so on plus 1. It definitely an integer and it is greater than 1. So the numerator a power pq plus 1 divided by a power p plus 1 gives a result integer. So the remainder should be 0. That is a power p plus 1 fully divides, that it divides a power pq plus 1. That means that a power p plus 1 is a divisor of a power pq plus 1. But pq is nothing but what? It is n. So a power p plus 1 is a divisor of a power n plus 1. So it leads to that a power n plus 1 is a composite number. Therefore it cannot be a prime number, which is a contradiction. Why it is so? Our assumption n is a combination of p and q where q is odd. So it is not possible. So n should be a power of 2. So hence theorem, there are infinitely many primes of the form 4n plus 3. We already saw in last module that what is Dirichlet conjecture. Dirichlet conjecture means there are infinitely many primes of the form an plus b, where a and b are positive integers. So here we are seeing a particular case. We are going to see the proof of this theorem. We know that any prime greater than 2 is either of the form 4n plus 1 or 4n plus 3. Again, by the Euclidean algorithm, if you divide any number by 4, there are only possible 3 remainders, that is 0, 1, 2, 3. So any number can be written as 4q plus r gives the result. For r equal to 0, it will be 4q, r equal to 4q plus 1, r equal to 4q plus 2, r equal to 3, 4q plus 3. But 4q and 4q plus 2 are divisible of 2, divisible by 2. So they are composite numbers. So the only possible prime numbers expression is 4n plus 1 or 4n plus 3. And also we observe that 4n plus 3 is an equivalent form of 4n minus 1. So now let us prove the proof. Let consider prime numbers 2, 3, 5 up to some p. Up to what we know the prime, let us choose the prime p. Now consider an expression q. The q is nothing but 2 square into 3 into 5 up to p minus 1. So 2 square is nothing but 4. So q is nothing but 4 times 3 into 5 up to p minus 1. So we observe that it is of the form 4n minus 1, where n is nothing but product of 3, 5 and so on p. And we know that 4n minus 1 is an equivalent form of 4n plus 3. So q is an equivalent form of 4n plus 3. And now we observe that Q is not divisible by any of the primes from 2 to up to P, that is less than or equal to P. So there should be a prime which is either Q or any other number which is a divisor of Q. So, and also we observe that next one. The product of any numbers of the form 4n plus 1 is again of the form 4n plus 1. So, Q is of the form 4n plus 3. If it is not a prime, it should have the divisor other than 4n plus 1. So, it should be divisible by a prime of the form 4n plus 3, which is greater than P. Since P is arbitrary, it follows that there are infinitely many primes of the form 4n plus 3. If Q is itself a prime, then there is nothing to prove because it is already in the form 4n plus 3. Hence, there are infinitely many primes. As Dirichlet said, it is of the form 4n plus 3 having infinite expression. There are infinitely many primes of the form 8n plus 5. This is also Dirichlet conjecture. Now consider the integer Q given by Q is equal to 3 square, 5 square, 7 square and so on, P square plus 2 square. Where P is any odd prime and Q is equal to 3, 5, 7 up P the whole square plus 2 square. Now 3, 5, 7 up to P are odd numbers because we know that 2 is the only even prime number. And also we will prove in the next result that the square of an odd number is of the form 8m plus 1. So Q is of the form, the first expression 3 into P the whole square is of the form 8m plus 1 plus 2 square is nothing but 4. So 8m plus 5. And also there is a result, that is, see, we observe that Q is of the form a square plus b square, where a and b are G series 1 because 2 square is an even number, 3 up to P the whole square is an odd number. So they are having G series 1, they are co-primes. So by a theorem, any prime factor of Q is of the form 4m plus 1, where m is any positive integer. Now consider two cases. If m is even, then m is of the form 2k. Then in this case, Q is of the form 4m, that the divisor of Q is of the form 4n plus 1, that is something but 8k plus 1. If m is odd, it is of the form 4m plus 1 is nothing but 4 into 2k plus 1 plus 1, that is 8k plus 5. So the divisors of Q is in the form 8k plus 1 or 8k plus 5. And again, we use the same argument that the next product of any number of the form 8m plus 1 is again of the form 8m plus 1, but Q is of the form 8m plus 5. So all the factors of Q cannot be of the form 8m plus 1. Therefore, there must be a factor of the form 8m plus 5 for Q, or either Q itself a prime. It is already in the form 8m plus 5. Thus, in either case, there exists a prime number of the form 8m plus 5 greater than Q. Since Q is arbitrary, similarly, we can construct primes in the form 8m plus 5 other than P. So this leads to the proof of the theorem, that is, there are infinitely many primes of the form 8m plus 5. Next, there is a simple result that the square of an odd integer is of the form 8m plus 1. So now consider n be an odd integer. So what is the general form of an odd integer? It is of the form 2k plus 1, where k is any positive integer. So we are considering the square, that is square of n square, that is n square equal to 2k plus 1 the whole square. It's we are well known aware of the formula a plus b the whole square, that is nothing but a square plus 2ab plus b square. So it leads us n square is nothing but 4k square plus 4k plus 1, and we can rewrite this as 4 into k plus 1 plus 1. And we already seen in model 1 that product of any or consecutive integer is multiple by, so that is divisible by or factorial. So here product of two integers, that is k plus 1. So it is divisible by 2 factorial, that is 2. So that is divisible by 2 means multiple of 2. So 4 times m of 2. M of 2 means multiple of 2 plus 1. So 4 times multiple of 2 means 4 times some 2 lambda, that is 8 lambda plus 1. So that is m of 8 plus 1. So this leads us that n square is nothing but some multiple of 8 plus 1, that is 8m plus 1. Next, prove that if P is a prime of the form 3n plus 1, then it must be of the form 6m plus 1. And we already seen a result that if P is greater than 3, then it should be of the form 6m plus 1 or 6m plus 5. Here we are saying that if P is a prime, if it is of the form 3n plus 1, it should be of the form 6m plus 1. Again, we observe that if P equal to 3m plus 1, it should be of the form, it should be odd prime. It cannot be even prime because we are known that 2 is the only even prime number. So P is an odd prime. It's let us if 3m plus 1 is odd only when n is even. So therefore we are taking n is equal to 2k, that is P is equal to 6k plus 1. The last result, prove that there are infinitely many primes of the form 6n plus 5. Again Dirichlet conjecture. So here we are considering integer q is equal to 2 into 3 into 5 and so on, p minus 1. We have seen already that 4n plus 3 and 8n plus 5. All these cases we are choosing an integer which is of the form that given prime, that is 6n plus 5 or 4n plus 3. So similarly we are considering here a number q which should be of the form 6n plus 5. So here we see that this is of the form 2 into 3 is nothing but 6. So it should be of the form 6m minus 1. We know that it is an equivalent to the form 6n plus 5 and know that it is not divisible by 2, 3 and so on p. So it should be divisible by any of the primes up to p or either q itself a prime. Suppose if q is itself a prime, then there is nothing to prove because it is already in the form. So suppose if it is not a prime, if it is divisible by some other number which is greater than p, then it should be of the form either 6n plus 1 or 6n plus y. Why it is so? Because we already told that if p is a prime greater than 3, it should be of the form either in 6n plus 1 or 6n plus y. And also again I am repeating the same argument that 6n plus 5 is equivalent to the form 6n minus 1. Next. So again if q is a prime, clearly it is of the form 6n minus 1, that is of the form 6n plus 5. If q is not a prime, it must be divisible by the primes of the form 6n plus 1 or 6n plus y, because the product of the numbers of the form 6n plus 1 is again of the form 6n plus 1, but q is not of the form 6n plus 1. So all the factors of q cannot be of the form 6n plus 1. There must be a chance for 6n plus 5 factor. So thus in either case there is a prime of the form 6n plus 5 which is greater than p. That is, we are choosing a prime p, and more than p we are finding some other prime which is larger than p. So similarly we can choose primes continuously. So therefore the primes of the form 6n plus 5 is infinite. Thank you.